Quantum mechanics, often described as bizarre and counterintuitive, continues to surprise us with groundbreaking discoveries. Among these, scientists have recently achieved something extraordinary. They observed atoms synchronizing their quantum states in free space without physical contact. This revelation challenges existing notions of quantum mechanics and opens new doors to technology and scientific exploration. The phenomenon of synchronization. Synchronization is a common occurrence in nature, such as birds flying in unison or fireflies lighting up simultaneously. However, seeing this collective behavior at the quantum level between individual atoms was once purely theoretical. At its core, quantum synchronization refers to atoms aligning their quantum states and acting in harmony as if part of a grand orchestra. Unlike quantum entanglement, which connects particles across space, synchronization is about a unified dance of quantum states, even in the absence of physical connections. The breakthrough experiment. The discovery was made possible through innovative technology and experimental precision. Ultra-cold atoms. By cooling atoms to temperatures near absolute zero, their quantum properties became more prominent. Optical tweezers. Using focused laser beams, researchers trapped and manipulated individual atoms in free space, isolating them from external influences. Light pulses. Carefully calibrated laser pulses were introduced to influence the atom's internal states. The results stunned scientists. These isolated atoms synchronized their quantum states, aligning energy levels and oscillating in perfect harmony. How synchronization happens. The key lies in quantum coherence, the property that maintains a consistent relationship between quantum states over time. Photons, the fundamental particles of light, acted as intermediaries carrying information between atoms. This photon-mediated feedback loop enabled the synchronization. Implications for technology and science. 1. Quantum computing. Synchronization could help overcome challenges like decoherence, where qubits lose their quantum states due to environmental interference. Stable and synchronized qubits could revolutionize computing, solving problems in chemistry, logistics, and disease research. 2. Quantum communication. Synchronized atoms could form the foundation of a quantum internet, enabling secure, instantaneous communication without physical connections. 3. Quantum sensing. The precision of synchronized atomic clocks could redefine GPS navigation and scientific measurement. These systems could detect gravitational waves, probe dark matter, and explore the universe's hidden dimensions. Philosophical and scientific implications. Beyond technology, this discovery raises profound questions about the universe. Does the synchronization of atoms hint at a deeper hidden order in nature? Could it support theories about multiverses or interconnected dimensions? Physicist Michio Kaku suggested this breakthrough might reveal new layers of reality, challenging our understanding of quantum mechanics and the cosmos. Challenges ahead. While promising, quantum synchronization at larger scales remains a significant challenge. Scaling the phenomenon from individual atoms to complex systems requires advances in theory, control methods, and technology. Furthermore, scientists still need to fully understand the underlying mechanisms driving synchronization. While our current simulations were able to reproduce the experimental data and explained why full synchronization cannot take place under current experimental conditions, a remaining open question is whether the phase transition could happen under different conditions and at higher densities, where our theoretical methods fail and instead a genuine quantum description is required, explains Ray. In physics, solving complex problems often requires the combined efforts of both theorists and experimentalists. Theorists develop mathematical models and simulations to predict how systems should behave. Conversely, experimentalists conduct experiments to test and challenge these predictions. This collaboration helps bridge the gap between abstract ideas and observable phenomena. Exploring quantum states in different systems. One of the big questions people are trying to answer is if it's possible to create entangled states in different atomic systems, explains Sana Agarwal, a graduate student in Ray's group and the paper's first author. In a cavity system, this is enabled by these collective all-to-all interactions, atoms interacting one-to-one, but in free space, that still needs to be clarified. A cavity system can be fine-tuned to drive atoms into specific quantum states. In contrast, free space systems are less controlled. In free space, there are many effects to look at, like interaction-induced frequency, says Agarwal. You also have emission into all possible directions, not just predominantly into the cavity system. So these effects are expected to change the physics in the system, and that's why we started looking into it. And indeed, we found it's quite different. The specific free space experimental conditions raised the question of whether the observed behaviors were truly superradiant or coincidental. To answer these questions, the researchers carried out a series of theoretical simulations using a model that accounted for each atom as a dipole, absorbing and emitting photons from the laser and the light emitted by the other atoms. This was an interesting challenge, as the number of accessible states increases linearly in the cavity, but in free space, it can increase exponentially with system size, Ray elaborates. In many cases, the interactions can be weak enough that simplified treatments are possible, but it was initially not clear if that was going to be the case in this experiment. A glimpse into the future. This quantum discovery heralds a new era of scientific exploration. It pushes us to rethink the fabric of reality and inspires innovations that could revolutionize computing, communication, and sensing. As researchers delve deeper into this phenomenon, the potential rewards are immeasurable. From ultra-secure communication to understanding the mysteries of dark matter, the quantum revolution has only just begun. The recent discovery of atoms synchronizing in free space marks a groundbreaking milestone in quantum mechanics, expanding our understanding of the universe and challenging our perceptions of reality. This phenomenon, where isolated particles exhibit collective behavior, opens new avenues of exploration in science, philosophy, and technology. But what does this synchronization truly signify, and how might it reshape our understanding of the cosmos? A new paradigm in quantum mechanics. At the quantum level, particles behave in ways that defy classical intuitions, manifesting properties such as superposition, entanglement, and wave-particle duality. The addition of synchronization to this list adds another layer of complexity. It suggests that even isolated particles can self-organize, as though governed by a hidden order. This discovery invites scientists to explore the possibility of a universal principle connecting all matter and energy. Could the universe itself operate as a kind of quantum symphony, where every particle plays its part in a grand cosmic harmony? The synchronization of atoms in free space raises profound philosophical questions about the nature of individuality. If particles can synchronize their states and act as a unified whole, are they truly distinct entities, or do they belong to a larger interconnected system? This idea challenges traditional notions of separateness and identity, with implications that extend beyond physics to fields such as biology, neuroscience, and sociology. Agarwal adds, "We considered a microscopic model in which every atom acts like a dipole and used it to study the emergent properties of the entire atomic cloud. The laser beam is a plane wave, imprinting a specific phase pattern on the atoms, which is crucial in determining how the atoms interact." The researchers simulated different conditions, including varying laser power and atom density, to see how these factors influence the system's behavior. Our simulation showed that a mean field approximation, which reduces the complexity greatly by treating the atoms as classical magnets, was enough to reproduce the physics, Ray notes. This model was validated with more complex approaches to ensure consistent results, confirming theories with experimental data. When we were comparing the theory with the data, we were unsure if it would agree, Agarwal says. Some of the data was fairly easy to compare because there was less ambiguity in the experimental apparatus. So when our findings agreed with those results, it gave us a vote of confidence that what we're doing makes sense. From their simulations, the researchers concluded that while the free space experiment agreed with the cavity model, within a narrow range of laser intensities and atom densities, the two systems generally behave very differently. Advancing understanding of quantum phenomena. These findings open new research avenues in quantum physics and validate the great value of experiment theory collaborations to gain a better understanding of the underlying physics. While our simulations were able to reproduce the experimental observations in the regime where the system is dilute, and the mean field approximation is valid, it will be very exciting to study new regimes where our current theory models become obsolete and better treatments are required, Ray adds. Our group will be looking for ways to improve our calculations and to prepare us for the new exciting measurements coming ahead. Biological parallels and interdisciplinary insights. In living systems, synchronization is a common phenomenon. From the firing of neurons in the brain to the coordinated behavior of cells in a developing embryo, nature demonstrates countless examples of individual components working together as a cohesive unit. Could the principles of quantum synchronization provide insights into these biological processes? If so, this understanding could lead to breakthroughs in medicine, neuroscience, and biotechnology. For instance, synchronized atoms might revolutionize artificial intelligence. Current AI systems rely on classical computing, which has inherent limitations. By harnessing quantum synchronization, scientists could develop AI systems that are more powerful, intuitive, and adaptive. These systems might mimic the brain's coherence, enabling advancements in robotics, natural language processing, and decision-making. Reconsidering the nature of reality. Synchronization also forces us to rethink fundamental questions about the universe. Could it serve as a bridge between the quantum and macroscopic worlds? For decades, physicists have sought to reconcile quantum mechanics with classical physics through theories such as quantum field theory and attempts at quantum gravity. Synchronization suggests the gap between these realms may not be as vast as previously thought. If atoms can synchronize across free space without direct interaction, it hints at an unseen universal mechanism fostering coherence across all scales of existence. This revelation could potentially pave the way for a unifying theory of everything, connecting quantum mechanics to general relativity. Such a theory might reveal entirely new dimensions of reality and offer a deeper understanding of the cosmos. Could quantum synchronization be the missing link in our quest to understand the universe's most fundamental principles? Applications in technology and beyond. From a practical perspective, quantum synchronization could revolutionize technology. Synchronized atoms might enhance quantum computing, communication, and sensing. These advancements could lead to ultra-secure communication networks, more efficient energy solutions, and groundbreaking medical devices capable of detecting diseases at their earliest stages. Synchronization may also have implications for space exploration. Synchronized quantum systems could enable the development of resilient spacecraft and instruments capable of withstanding extreme environments. This technology would open new frontiers, allowing humanity to explore distant planets and star systems. Philosophical and ethical implications. The discovery of quantum synchronization raises ethical and philosophical questions about individuality and interconnectedness. If particles are part of a larger unified system, what does this mean for concepts like free will and identity? Some philosophers draw parallels between synchronization and ancient spiritual ideas of oneness, suggesting a scientific basis for the interconnectedness of all things. As we harness this phenomenon, it's crucial to consider the ethical implications. How do we ensure quantum technologies are used responsibly and equitably? How do we address potential risks and societal impacts? The dawn of a quantum revolution. Despite the challenges, the discovery of quantum synchronization heralds the beginning of a new era in science and technology. It's a testament to the boundless potential of human curiosity and ingenuity, revealing the hidden order that connects us all. From the smallest particles to the largest cosmic structures, synchronization offers a transformative lens through which to view the universe. As researchers delve deeper into this phenomenon, they'll likely uncover new insights that reshape our understanding of reality. This discovery is not just a scientific breakthrough. It's an invitation to embrace the unknown and explore the infinite possibilities of the quantum world. In the end, quantum synchronization is more than a revelation. It's a call to reimagine the universe and our place within it.